All right, so this is a covering chapter 18 practice exam, question 18, and then also question 12. Okay, so pH at the equivalence point for hydrocyanic acid. So there's kind of two ways you can do this. The long way would be to remember that moles of the acid equal moles of the base at the equivalence point. And I think I'll go ahead and do it this way just because it will connect with what we've been doing in class the best. Okay, so for the acid, we've got 0.2 molar and 10 mils. For the base, we have 0.150 molar, and we don't know what the volume is. So I'm starting by trying to find the volume so that I can then do the consumption step, the dilution step, the consumption step, the equilibrium step. Okay, so solving this one, I get that the volume of the base is 13.33 mils. So often the question is, what's the equation? So with a titration, you're of HCN and you're adding a strong base. I'm going to not write the Na plus because it is not useful. It doesn't matter. It's just going to sit there. So feel free anytime you're dealing with a strong base to just ignore that and start it off as OH minus. In fact, if you're working with a strong acid, you can do that with the minus side and just call it H plus. I just did another video about how to write these equations and talked about this as well. Okay, so these guys combine and form CN minus and water. So we're going to do the dilution step first. Probably going to have to give myself a little bit more room here. So 10 mils of HCN, 0.2 molar, and now there's a total of 23.33 mils. For the OH minus, it's 13.33 mils, 0.15 molar, and 23.33 mils. Okay. All right, so the initial concentration of the HCN is 0.0857. And this is 0.0857. This will happen every single time you're at the equivalence point. That's the whole point, is that all of the HCN is going to react with exact right amount of OH minus because they're equal. The moles of the acid are equal to the moles of the base. Sorry, I don't have a drink of water. So I can't subtract the smallest because there isn't a smallest. I just subtract. Both of them come out to be 0. And the CN minus, we didn't have any to start. And we actually add. All right, excuse me, just 1 minute. We actually add 0.0875. So what happens at the equivalence point is that all of the acid gets converted to the conjugate base. So in this example, we don't have an equilibrium step that we can use the Henderson-Hasselbalch because the Henderson-Hasselbalch assumes you have some of the acid and some of the conjugate base. So for the equilibrium step here, we're just going to have to do an ice table. Oh, it's not going to, I don't have room for it. Let me switch over to a separate one. We're going to have to do an ICE table with CN minus, because equilibrium means we have to have a K, and the only compound we have, goodness, the only compound we have is the CN minus. So we're going to do the KB. So we're going to, what did I say? 0.0857, right? 0.0857. 0 of this, 0 of that. Minus x plus x plus x. KB is equal to x squared over 0.0857 minus x. I guess I do need to figure out what the KB is before I say that that's small enough that I don't have to worry. So the question tells me that the pKa is 9.31. It's interesting. I'm not sure why it puts it in those terms, but whatever. That means that the pKb is 14 minus 9.31, or 4.69, okay? And the KB would be 10 to the negative 4.69. There's probably an easier way to do this. It's just not coming to my head right now. This particular part. Maybe I'll figure it out in a second. Okay, so the KB is equal to 2.04 times 10 to the negative fifth. Okay, so we can ignore the minus x. And our equation now is x squared over 0.0857 is equal to 2.04 times 10 to the negative fifth. When we solve for x, that's going to be equal to the OH minus. And so the pH will be 14 minus the negative log of x. Okay. There was something, yeah, I can kind of see how they could have done it a little bit easier with the pKb, but I'm not going to mess with it. This is just fine. Normally, I would just give you the Ka or the Kb. Remember, the Ka and Kb are related through Kw, which is 10 to the negative 14th. So Ka times Kb. So you can always use that as well. I used pKa plus pKb is equal to 14. Okay. All right, so x here comes out to be 0.132. So I get that the pH is 13.12. Ooh, that is weird. 132. Okay. Let's see. Obviously, I did something wrong somewhere because that answer is not on there. Ugh. Okay, let me just double check the math real quick. It's going to be annoying because I don't know if I know how to pause the video. Maybe I can edit it out. Oh, there was some zeros in there. I just found it. It was this value should be 0.00132. I think I must have missed a zero up there when I did it. It's always something like that. Okay, so 14 minus -1 log 0.00132 is 11.12, which I believe is in there. Yep. Okay, next one was, this is 12, so the next one was 8. No, this is 18, sorry. Next one was 12. All right, you've got a 1 liter buffer solution and you add 0.035 moles. This one's actually kind of nice because you're adding moles, not a volume with a molarity. So you don't have to dilute it at all. All you have to do is find out the concentration of the NaOH. So you're going to find out the molarity by just doing moles per liter. Moles per 1 liter, right? So 0.035 molar. Okay, so it's a buffer. You've got 2 compounds and you're adding a strong base. So we're gonna, this was our dilution. This is the only thing we had to do for a dilution step. We're gonna now do a consumption step and then an equilibrium step. Because we're adding base, so I'm just gonna write OH minus, I'm not gonna write the Na. I have to add that to the acid that's part of the buffer. Okay, that will then make the conjugate acid, or sorry, the conjugate base. Now, I again didn't write the sodium. You either have to write it in both places or not write it at all. So you could have written it here and you just wouldn't have the minus, and then you could have written it here without the minus. I prefer to just take off those spectator ions because I think, especially for you guys, I think it is less confusing. Okay, so we did the dilution. We're doing the consumption. So this is 0.035. We calculated that up there. They tell us this one is 0.1 and they tell us this one is 0.1. The big difference with buffers is that you have some of that conjugate, either acid or base already. In a titration, you don't have any of that yet. Okay, then we use the smallest one up, 0.035, and we add it to that side. Okay, so I get 0, and then this would be 0.065, right? 69, yes. And then 0.135. Okay, now third step, equilibrium. pH equals pKa. So we're going to take the negative log of 1.8 times 10 to the negative 5th plus the log of base, 0.135 over acid, 0.065, and that should give us our pH. Okay, so that is equal to 5.06, which it doesn't tell us initial pH, so I don't have a good gauge of how correct that is, but it looks pretty good. All right, all done.